Hi everyone. Up to now, you should have looked at sampling and types of data and graphical summaries. In this session, I'm starting to look at numerical summaries of datasets. Now, first of all, we're looking at measures of location. In other words, measures that tell us where the data is situated on our number line or x-axis, or where most of the data is located, maybe where the middle point of the data is located. So the first thing that you must consider will be the definitions, very important. Then the purpose of these summaries, which summaries is best for which types of data. You must be able to calculate these numerical summaries, and then the most important, extract information. Right, so extracting information is really right up there with knowing the definitions. Now, before we look specifically at measures of location, I just want to quickly overview the four numerical summaries that we will be discussing. The first one will be the measures of location. The next one will be the measures of spread. In other words, how the data is spread on the x-axis, or the horizontal axis in our case. And the third one will be the skewness, so how symmetrical is the data. And the last one is called kurtosis, which is a method for determining whether we should expect any outliers or any extreme values in the data set. Now, the measures of location that we'll be looking at, there's three of them, the mean, median, and the mode. So in this little illustration here, we see three frequency distributions, or three distribution curves, but they are in different locations on the horizontal axis. Next one, measures of spread. Here are the measures that we'll be considering. And the little image over here, we can see that all three of these are on the same location on our x-axis, but they have different spreads. So for this middle one over here, the data is spread over a smaller area than the outer one. Then the skewness is something that we just encountered in the previous section. This one over here, where we have few values that are really, really small, and the bulk of the values will be to the right, in other words, large values. We say that this thing is skewed to the left or negatively skewed. This is the opposite, positively skewed or skewed to the right. Right, and then of course kurtosis will simply be trying to determine whether we do in fact have extreme values sitting at the ends over here. Right, now one definition that I just want to remind you of that's going to be coming up now again is the difference between numerical summaries for populations and for samples. When we talk about summaries for samples, we talk about statistics. When we talk about summaries for populations, we talk about parameters. So when you hear parameters, you know that I have used a population to do my calculations for, and when I talk about statistics, you must know that I used a sample to get the data for my calculations. Right, so let's jump in and look at what each of these methods do. So measures of location. Let's consider a data set, and the data over here, these values were recorded in no specific order as they were observed. They were actually just written down. We have 20 of them, so the subscript goes from 1 right up to 20. This variable has a name capital X. If you go back to data, you will see where this is coming from. So we'll call the variable capital X. Every single value that variable can take will be a lowercase x with a subscript or an index to tell us which one we're looking at. So x1 will refer to the value 0, x2 to 260, x3 to 220, all the way to x20, which refers to 180. The three statistics that we'll be calculating will be the mean, median, and the mode, which are the three measures of location. Now, first of all, the mean is sensitive to skew data. In other words, it is not robust. Okay, sensitive to skew data means that skew data will affect the interpretation of the mean, because the mean is supposed to give us a certain measurement that tells us something about where the data or the bulk of the data is situated. But if the data is very skewed, the mean is not a reliable measure of location. Now, the way in which we calculate the mean is just an average, an arithmetic mean, so you have encountered this before, definitely. First of all, we denote it by x bar. Okay, the mean is denoted by x with a bar on top of it. It will simply be the sum, which is this sigma notation over here. It's the sum of all the x's, and we divide by the total number of values n. So for our example, we will be adding up 20 different values and taking that total and dividing it by 20. So we're adding up the values, dividing by 20, and we get 186.0. Right, so this is my average for the data set. Right, next one is the median. The median is the middle point of the data. It is not sensitive to skew data. So in other words, it is robust. So that means if we have extreme values in the data set, or if the data set is skewed, it's not going to affect the reliability of the median. The median will still tell us what it's supposed to tell us, but the mean, it will not be that reliable for skew data. So if we have skew data, or data with outliers, the median is actually a better method to use to indicate location instead of the mean. Now, I said that the median is the middle point of the data. Now, to find the middle of anything, you need to know where it starts and where it ends. So if we look at the data set, then what we need to do is we need to arrange the data from smallest to largest. So the smallest value of my data set was 0, and the largest value was 290, and everything else will be arranged accordingly. Now, you will notice that I'm not using x's, I'm using y's now suddenly. But I still have a subscript y1 up to y20. And this data set now will be called capital Y. The reason for this is that arranged data can't have the same name as the raw data because we've processed it. And usually, if the raw data is denoted by x's, then the arranged data will be denoted by y's. So in this case, y1 is equal to x1 because it's 0. However, if we look at this case over here, y20 is not equal to x20. y20 will be 290, but not the first 290 either, it will be the second one. So it seems to be this value over here, x13. So y20 is equal to x13, and y19 will be equal to x10. Okay, so that's how the y labels work once we've arranged the data from smallest to largest. Now the way in which we denote a sample median is by x with a little squiggle on top, which we call a tilde. Okay, so it has a little squiggle on top of it. When you see that, you know it's the median. If it has just a straight line above it, you know it's the mean for the sample. Now, first thing is that the median is the middle point. Now, this calculation over here will be for when we have an even number of observations, like we do in this case, we have 20 observations, and this one will be for an odd. It's very easy to actually find it. The middle point, we'll count 10 from the left, and we will count 10 from the right. So here we'll have the middle point of the data. Now the middle point is not on a value because we have 10 to the left and 10 to the right. So what we'll do is we'll take 200 plus 200 divided by 2, which is still 200. But the point is we'll take the average of those two middle values because we don't have a single value sitting over there. We'll take the average of the middle two. Right, the mode, also not sensitive to skew data. The mode is also the only measure of location that can be used for qualitative data. And why is that? Because the mode is the value that appears the most. So we simply look at the value that appears the most for quantitative data. If it's qualitative data, we look at the label or the category that appears the most, and that will be the mode. So for our example, the mode will be 220 because that appears 3 times, whereas the other values, I think the most is like 200 that appears twice, 290 that appears twice, 125 that appears twice, 170. Right, so the mode appears 3 times, 220. It's also easier to find the mode once you've arranged the values in ascending order because then all the same values are grouped together. Right, now for group data, the calculation becomes a little bit messier. For group data, we don't have the raw data. We don't have the individual observations. So how do we calculate an average if we don't have the individual observations? How do we calculate a median if we don't have the individual observations? And the same for the mode. So there's other formulas that we need to use in order to get these 3 results. For the mean, we're going to be using this. Now, this looks almost like the previous one that we had, but the slight difference is now with this f that's in here, which is just the frequency. So what this is actually saying is that we don't have the individual observations in my data set over here, right, in my group data in the table. I know that there's one value in the interval negative 0.5 to 58.5, but I don't know what that value is. I know that there are 8 values in the interval 176.5 to 235.5, but I don't know what those 8 values are. So what this formula is saying is it is saying take the midpoint for each of these classes and imagine that all the data is equal to the midpoints. So the one value that's in this class, imagine that it's equal to the midpoint. So I have a value equal to 29 in the first class. The second class, I have one value that's equal to 88. The next class, I have 6 values that's equal to 147. The next one, I have 8 values that's equal to 206. And the last one, I have 4 values that's equal to 265. And now calculate the average using that. So that means I still need to add everything together, but they're not going to be raw data, they're going to be midpoints now. So I'll take 29, one of them, plus 88, one of them, plus 147, 6 times, plus 206, 8 times, plus 265, 4 times. And that's where this frequency comes from. We're simply saying take the midpoint, multiplied by the frequency, add all of it together, and then divide by 20. And that's exactly what we did. And we get 185.4. Now the previous average, which you probably don't remember, but I do, that average was 186. And this was for raw data, whereas this one is for group data. Now why is there a difference? Well, here we had the actual observations, but here we don't. We use the midpoints. So this one for group data is actually an estimate. It's not the real. If you look at the median calculation, then it is very messy compared to the previous one. The previous one simply said, arrange the data from smallest to largest, find the middle point. If there's no single value in the middle, and you have 2 values in the middle, then you take the average of those 2. But in this case, we need to use this miserable looking formula. So let's see. The first term in this calculation will be LM, which is the lower boundary of the median class. Now, the median class will be the class that contains the middle value. Now, I don't know what the values are because I don't have the raw data, but I can identify the class that will have the middle value. I have 20 observations in total, cumulative. Okay, so 20 observations in total. In the first class, I have 1 value. By the second class, I'll have 2. By the third class, I'll have 8. And then in the fourth class, by the end of the fourth class, I have 16. So when I start the fourth class, in other words, when I enter the class over there, I enter it with 8 values that I have from the previous classes. When I exit this class, I have 16. The middle point is at 10 and 11. So that means in here, I'll have 10 and 11. So the median class will be class 4, and the lower boundary of the median class will be 176.5. The next one, cumulative frequency of the classes before the median class. When you see a capital F, when we work with group data, it always refers to cumulative frequencies. Lowercase f will be the relative frequencies. Right, subscript m-1, which means the class before the median class. So we've identified class 4 as a median class. Class before it will be 3. We need the cumulative frequency of that class, so that means we will need 8. That'll be my f m-1. The next one is the frequency of the median class, fm. The median class, where is that? Well, it is class 4, because remember, when we entered this class, we had 8 values, that 8 over there. When we exited this class, we had 16 values. So the middle point, 10, 11, is somewhere in here. So the frequency of the median class will be 8. And the last one will be the class width. Now that's easy enough. We simply take any upper boundary minus the lower boundary for that class. And we see that in this case, if I take 117.5 minus 58.5, that gives me 59. So now we just simply plug it in there and solve, and we get 191.25, which again is not the same as the median for the raw data, just like the average case. Now next is the mode, which is also a terrible looking formula that we need to use, a lot more complicated than for raw data, where we simply just count. Right, so here we have a few different values as well. We have the lower boundary of the modal class. Now the modal class is the class that has the highest frequency. So 8 is the highest frequency, and that is for class 4. So the lower boundary of the modal class is this 176.5. Next one is the frequency of the modal class. Well, the modal class is still this class 4, so the frequency will be 8. Then the frequency of the class before the modal class. So this is it. It will have a frequency of 6, then plus 1. So that will be the frequency of the modal class, frequency of the class after the modal class. So that will be 4. And then the class width, which again can be any upper boundary minus the lower boundary. So if you take that minus that, it's 59. If you take that minus that, it's still 59. Substituting all of that and solving, we get 196.17. And again, this is an estimate because it comes from group data. Okay, so it's an estimate because of group data, whereas the original one will be the actual value because that comes from raw data. Okay, and the original one, if I remember correctly, was 220, and this was from the raw data. Right, so for group data, we can calculate the 3 measures, but it's a little bit more complicated than for the raw data. And because we use the midpoints, we don't have the raw data. For group data, we'll call the results the estimates, whereas for the raw data, it's the actual values. Remember the advantages and disadvantages of the 3 methods. For the mean, we said that it is not robust. In other words, extreme values will affect the mean and affect its reliability. The median and the mode, that's a little bit more reliable when we have skew data. The same properties will hold for group data because it's the same measures. Right, now here we have, instead of a sample, we have a population. Now we're not going to have a population of group data. We're just going to have a population of raw data. And you'll see that it is actually the same data that I had before, but I've just called it now a population because there's only 1 or 2 small things that change when we go from calculating statistics for a sample to calculating parameters for a population. If we look at the mean, it's still the same property. It's sensitive to skew data. But now, if we look at calculating the mean, then we see that we don't have an X bar anymore. We have this thing. Now this thing is called mu, mu. That's a Greek letter. And when you see mu, you must immediately think of an average for a population, because that's what it represents in statistics. And because we're working with a population, we are adding all the values in the population. So the total number of elements in the population is denoted by capital N, not a lowercase n. But the actual calculation remains exactly the same. It's just lowercase changes to uppercase, and X bar, which was the sample, that changes to mu, which is for a population. For the median, you can see the difference here. Again, capital N come into the calculation, and now we have this thing that looks like an N, but it has a longer tail on the right. This is called eta, and it's also a Greek letter. So if you see this eta in statistics for summarizing data, then you know that it refers to the median of the population, whereas the median for the sample will be X with the squiggle on top. Okay, the tilde on top. This is the median for the sample, this is the median for the population, and the population size will be capital N. And then lastly, the mode. This is actually a very nice one. The mode stays the mode. There's no short notation for it. It's just the value that appears the most, so we simply just go through the population and we count, and that's it. So, to summarize, what we have in this case is for population data, we only have raw data. We don't have group data. Okay, so no group data for a population. Only raw data. The formulas are exactly the same as for the samples. However, the notation is new. The mean is now denoted by this U with a long tail on the left, which we'll call mu. The median is eta, which is almost like an N but with a long tail on the right, and the mode stays exactly the same. So this mu and eta we will call our population parameters. Now, if we look at graphically what this means, the 3 values that we just calculated, then we had raw data, doesn't matter whether it's a sample or a population, and we have group data, which of course will just be for a sample, and the parameters that we calculate for the population and the statistics that we calculate for the sample were these values. Now for the group data, we had the 185, 191, and 196. For the raw data, we had different values, 186, 200, and 220. And that's because we actually had raw data which gave us exact results. For the group data, we had to use the midpoints as estimates, and that's why we get results that are not exactly the same. However, the differences will not be that big, first of all, and secondly, the relationship between the values will stay the same. So usually if the median for the raw data is bigger than the mean, then you will have the same result for the group data, for the estimates. But the most important to take away from this is actually what it means. We saw that this data is negatively skewed. In other words, the curve looks like that. It has a high peak on the right, and it has a tail, a longer tail on the left. So it's negatively skewed. We can also say that it is skewed to the left. And when we have data that looks like this, then this will be the relationship between these three values. The mean will be the smallest, the median will be in the middle, and the mode will be the largest. If we have negatively skewed data that's unimodal, right? Unimodal, one peak. So if it looks like this, then this is going to be the relationship. Small mean, median in the middle, and a larger mode. And that's the most important to take away. For symmetrical data, the mean will be basically the same as the median, and that will be basically the same as the mode. All three of those values will be in the middle here somewhere for symmetric data. For positively skewed data, the mean will be the largest, so this is going to be the mean. The median will be in the middle now, so this is going to be the median, and the mode is going to be the smallest value. That's going to be on the left. The mode is the value that appears the most, so the highest peak. Negatively skewed is the example that we looked at. Here the mean is going to be on the left, and the mode is going to be on the right, and the median is still going to be in the middle there. Right, so this is the most important to take away from this whole section. If we have data set, or data that has a single peak, right, so it's unimodal, then when we calculate these three values, mean, median, and the mode, the relationship between them will tell us something about the shape of that unimodal data set, whether it's a population, whether it's a sample, whether it's group data, whether it's raw data. It doesn't matter. The relationship will remain the same.